All right, logistic equations is what we're going to be talking about today, and logistic functions are a way of describing growth of populations. In logistic growth, the growth of a population is proportional to the population and the carrying capacity, M. Carrying capacity is going to be what the maximum population could be, okay? And so that gives us this differential equation, dp dt, which is the rate at which the population is changing with respect to time, is equal to kp times m minus p. Now, we could do separation of variables and solve this equation for p, which we're not going to go through that whole process right now, but that solution equation ends up being this right here. And so P is equal to M, which once again is the carrying capacity, over 1 plus C, which is a constant, times E raised to the negative M, so that's the same M, times K, which is another constant, times T, which is time. And this is one set of differential equation with its solution. There is another version or form of that also, and that is this one right here. This is the one I tend to use most often. dp dt is equal to kp 1 minus p over m, and the solution for it is this. Now the only difference here, how we get from this equation to this equation, all we're doing is factoring out the m. If you factor m out of this parenthesis, that's going to leave you with 1 and p over m right here. Now this k value is a constant. This k is not the same numerical value as this k. This k is actually achieved by multiplying m times this k value. All right, so just keep in mind this k value is not the same k value as this one is right here. All right, so let's go ahead and take a look at a specific example here. A rumor is usually spreads logistically. A rumor spreads as tellers pass it on to the hearers. Once the rumor is told, a hearer becomes a teller. The rumor spreads slowly at first, when tellers are few and the room for growth is large. As time passes, there are more tellers and the room for growth is smaller, but the product of these two numbers is larger than it was before, so the growth of the rumor is faster. As time increases further, the number of tellers is plentiful, but the room for growth is small. So their product is small. So the growth of the rumor is now going to be slow again. So this curve is going to represent your population growth. A school has 1,300 students. 25 students start a rumor that the school is going to be replaced with a new one. A day later, 65 students know the rumor. Write the differential equation that describes the situation and then solve it. Then determine how many students have heard the rumor after 7 days. All right, so the differential equation, let's go ahead and start right there. The differential equation is going to be dp dt is equal to k times p times 1 minus p over the carrying capacity. The carrying capacity is the maximum number of students that can hear this rumor. Since there are 1,300 students, that is your carrying capacity. Now, we do not know the value of k in this, and we do not know the value of p. Well, p is going to stay in our problem because it's going to be part of our equation, but we need a value for k, which we cannot find because we don't know anything about the rate at which the population is growing. So we're going to leave this equation alone for a minute, and we're going to go straight to the solution equation. And the solution equation is going to be P is equal to carrying capacity, 1,300, over 1 plus CE raised to the negative KT. Now, this equation has two values in here, C and K, which represent constants. We need to find the values of these two things. In order to find the values of those two things, we need some numbers or coordinates or whatever you want to call it that we can put in for T and for P. And so the values that we're going to do is we're going to use the 65 and the 25. So it says that 25 students started a rumor, so if we think of that in terms of a coordinate, that would mean P of 0 is equal to 25, or in other words, when T is 0, we add 25 students. It says a day later, 65 students now know the rumor, so that would be P of 1 is equal to 65. All right, so let's start with P of 0 equals 25 and substitute those values into our equation. All right, so that's going to give us 25 is equal to 1,300 over 1 plus CE raised to the negative K times 0, which is 0. And e to the 0 power is 1, so I can really just take that part off, giving us this. Well, that now gives us a way of being able to solve for C. All right, so what I'm going to do is multiply the denominator over to this side and divide 25 over to this side. And that's going to give us 1 plus C is equal to 52, which means C is 51. All right, I can now plug the value of C, which is a constant, so it's not going to change depending upon anything. It's always going to be 51. So we're going to have 1,300 over 1 plus 51 e raised to the negative kt. All right, so now we want to find the value of k, that constant, in this problem. We're going to use the other coordinate. P of 1 is 65, so that's going to give us 65 is equal to 1,300 over 1 plus 51 e to the negative 1 times k, which would be negative k. All right, so we'll do the same maneuver we did over on the other problem. So we're going to multiply the denominator over to the left, divide by 65, giving us 1 plus 51 e to the negative k is equal to 20. If you subtract 1 and then divide by 51, you're going to get 19 over 51. Take the natural log of both sides, so negative k equals natural log of 19 over 51, and k is now the negative natural log. All right, so we now know the value of k. We can substitute that back in, and that's going to give us P is equal to 1,300 over 1 plus 51 e to the negative k, so negative natural log will be natural log 19 over 51 times t. Now, the question up here says, determine how many students have heard the rumor after 7 days, which means we're just simply going to plug 7 in for t. And if you work all that out, we'll just say you're going to be doing it on the calculator. This comes out to 1,237.154. Naturally, you cannot have decimals of people, so really it's approximately 1,237 students have heard the rumor after 7 days. Now, also with this k value here, remember that we can substitute this back into here to get our differential equation. All right, so we're going to carry this new equation over to the next page, giving us this equation here. And if we distribute this natural log, that's going to give us dp dt is equal to natural log of times p of 19 over 51 minus natural log of 19 over 51 p over 1300 squared on this. All right, so let's take a look at what this question is asking. It says, we are usually interested in when the rumor spreads the fastest. We know the rate at which the rumor is spreading, and we wish to maximize, because we want to find out when this is going the fastest. So we're going to maximize this, which means we need to take its derivative, because you find a relative maximum by finding out when the derivative changes from positive to negative. So what we need to do then is we need to find the derivative of this will be our second derivative. And so that's going to give us d2p over dt2 is equal to natural log 19 over 51 minus natural log 19 over 51 p over 650. We would set this equal to 0, giving you negative natural log 19 over 51 p over 650 equals negative natural log 19 over 51. You can divide natural log to the other side, which is going to give us 1, or in other words, p is equal to 650. So if we do a sign chart with this and we substitute values larger than 650 into our second derivative right here, if we substitute values larger than 650 into here, this fraction becomes larger than this number. Therefore, you're going to get a negative value. And smaller numbers are going to give you a positive value. So this is your second derivative sign chart. So that means your derivative, or your second derivative, changed from positive to negative, which means your first derivative is reaching a relative maximum when 650 students have heard the rumor. All right, now the other thing to think about here with second derivatives is this is second derivative positive, which means your graph is concave up, second derivative negative, which means your graph is concave down, which just goes back to your logistic curve right here. This is 650. This would be your starting population of 25 students who started the roomer. Our carrying capacity up here was 1,300 students. Notice that 650 is half of our 1,300 students. Your concavity of your graph changes at that value. Concavity will always change from concave up to concave down, which means this is a point of inflection that always occurs at half of your carrying capacity. All right, so in logistic growth, the population always grows fastest when the population is half the carrying capacity. That's an important concept to make sure that you have right there. And however, that does not tell you when the population grows the fastest. In order to find out that, we need to set the logistic equation equal to half the carrying capacity. So for this particular problem, we're going to find when the roomer spreads the fastest. And the key word is when, which means we are looking for t. Now, your solution equation was p, which is our population of 650, equals 1,300 divided by 1 plus 51 e raised to the natural log 19 over 51 t. And we need to solve for t in this particular equation. All right, so we're going to do like we've done before, multiply the denominator over and divide by 650, giving us 1 plus 51 e to the natural log 19 over 51 t equals 2. And then we're going to subtract 1 and divide by 51. Subtracting 1 is 1, divided by 51 gives us 1 over 51. Take the natural log of both sides, which will give us natural log of 19 over 51 t equals natural log of 1 over 51. Well, what that is going to give us then is t is equal to natural log 1 over 51 divided by natural log 19 over 51, which comes out to about 3.982 days. So at basically 4 days, your carrying capacity is going to be half of that, or your population is going to be growing at the fastest rate. And we started at 25, which would be down here somewhere. And so we can think of our curve being concave up until that point. 1,300 is our carrying capacity, so we are concave down from that point forward. And that would be a sketch of our logistic growth curve. All right, so at this point, we're going to stop this video and call this part 1. And you can look for part 2 to continue with the notes.